Now I request Bera sir to start the presentation. Before asking him to join, let us see his profile. Already I have shared with you. He's having vast experience in topics such as quantum complexity, graph algorithms, privacy issues, and currently he's working as associate professor in Indraprastha Institute of Information Technology, New Delhi. I welcome Bera sir to start the session and address the participants. Sir, you are welcome. You can share your screen.
Okay. Am I audible?
Yes. Yes, sir, you are audible and your presentation is visible also.
Okay. Good evening, everyone.
Good evening, sir.
Good evening. So you had some, I joined a few minutes early and you had very interesting discussions. You should have continued with that. Very nice questions you had, and yeah, very insightful answers were also given. Okay.
This is
so
yours is the fourth session, sir. All the three sessions we really enjoyed, and I hope we are also going to enjoy your session also. Please
right.
carry on, sir.
Yeah. So unfortunately, I have been given the task of covering Shor's algorithm, which cannot be done without a due share of linear algebra and quantum algebra manipulations of states and things like this. So I'll try to give you some insights which do not require too much quantum before, and then maybe I'll dive into a little bit more technical details in the second half of the talk. Okay, so let's get going. Okay. Okay, so the topic of the session is Shor's algorithm and quantum cryptography. I decided to flip it and first tell you a little bit about quantum cryptography, and then from there move to Shor's algorithm. So in general, turn this on. Yeah. So in general, cryptography is what drives modern e-commerce, secure communication, all kind of things. And you all know that cryptography can be broadly two types: public key and private key cryptography. Public key cryptography and private key cryptography. Okay. So again, these are things that you already know, just so that we are on the same page. I'm just saying these things out. Okay, so in private key cryptography, there is a secret key, and there's a protocol that uses the secret key to encode a message, and then the same secret key is used to decrypt a message. And in public key, there are two keys. There is a public key and a private key. The public key is known to everyone. The private key is known to only one of the parties, and everybody performs an operation using the public key, and then the person with the private key can undo that operation, right? So depending on if you're doing encoding, digital signature, whatever. So one step is done by the public key holder, which is everyone. The other step is done by the private key holder. So and both of them are used in tandem in today's world everywhere. So let's see why do we believe that they are secure? Okay. So both of them are studied very well. They studied very well. So why are they secure? So secret key cryptography, their security comes from several information theoretic arguments, and okay. So because you probably already know why are they secure. Let me tell you what happens if quantum computers are there. What is the effect of a quantum computer on private key cryptography, and what is the effect of a quantum computer on public key cryptography? So for a private key cryptography, right? So one way to model a private key cryptography is you have a message, and there is a protocol, there is an algorithm, okay, and the algorithm also takes in a key K, and it outputs a ciphertext. Okay, so your C is basically your algorithm on your message and K. Okay, so so one way to break the system is to try all possible K. Suppose you have a message and a corresponding ciphertext. You can just try all possible K, searching for all possible K, and then whatever K matches, then you know that this is the key. This is the right key. So classically, this is very difficult because the key space is very large. So is there right? And that's what we believe that the security, the basis of the security is the fact that key space is very large. So, for example, suppose my key K is 1024 bits, then key space is the set of basically the set of all possible keys. That space contains 2 to the power 1024 possible keys. Okay. So key space is very large. You have to search among a lot of keys, and 2 to the power 1024 is more than the number of particles in the universe. So you know that this is quite good. Okay. So now what happens if there is a quantum computer? Well, I believe there was a session on Grover's algorithm earlier, or maybe you will see an algorithm later in one of the later sessions. So Grover's algorithm is a quantum algorithm that can search in a large space in the time that is square root, that's proportional to the square root of the size of the space. So Grover's algorithm, so the size of the space is 2 to the power 1024. So Grover's algorithm, so classically, if you want to search this space, the time you need is proportional to 2 to the power 1024 steps. Okay. Whereas if you use Grover's algorithm, what you need is square root of this many steps. So square root of 2 to the 1024, right, which is 2 to the 1024 to the power half, which is 2 to the power 512 steps. Okay. So the concept, so the idea of steps should be put in quotes because they're different. The steps in the Grover's algorithm, they're quantum steps. The steps in the classical algorithm, they're classical steps, but nevertheless, they somehow correspond to the time taken. The Grover's algorithm, as you can see, this is a drastic reduction. Right? This is more than half. This is a huge reduction. This is a quadratic reduction in the number of steps. So that's the advantage that a quantum computer can bring in sort of breaking your private key crypto systems by allowing you to do a brute force search with quadratic speed. And then you'll see this term quadratic speed up in many instances where when it comes to quantum computing, quantum algorithms, and they all somehow are related to Grover's algorithm. So this is the effect of Grover's algorithm on private key cryptography. Okay. So right, so whenever we can run Grover's algorithm on large enough qubits, we will be able to break our large crypto systems like AES, SHA, and MD5, and all those things. So that's the effect of quantum computing on private key cryptography. Now this is separate cryptography. Okay. So now let's move to private key cryptography. Okay. So okay. So now private key cryptography. Sorry. Let's now move to public key cryptography. So, so most of the public key cryptography, most of the e-commerce today, the public key cryptography that they use, they are so the security of public key cryptography. It's very surprising. It comes from certain assumptions. That is, we don't really know if the public key cryptography, the systems that are currently in place, they're actually secure or not. But there are two problems, two mathematical problems, which we believe are very hard to solve for classical computers, and public key cryptography is based on that. You probably are aware of both the problems. If not, definitely you are aware of one. So one of the problem is discrete log problem, and the second problem is factoring problem. So all the public key cryptography, most of it, at least 95% of it that's currently being used, they all are based on either the discrete log problem or the factoring problem. So let's first understand these problems, and then we will try to discuss why why do we believe that they are difficult. So what is the discrete log problem? So take a prime, take some large prime P, okay, and take some A and X, okay, from let's say 1, sorry, not even 1, 2 to P minus 1. You choose them randomly, okay, and then you compute B, which is A to the power X mod P, okay, and now you make PAB public, and X is the secret. Okay. Roughly, this is how the scheme. There are some details there in the actual implemented protocols, but this is roughly how the scheme works. Okay. So PAB are public. The prime number is public. The number A is public. The value that you get by raising A to the X is public, but the exponent, the power of A itself, the power is secret. Okay. And we believe, so there is a belief that given PAB, computing X is exponentially hard. There is no polynomial time algorithm can compute X. So now if you notice, if I did not have the mod P, then you could simply take log B to the base A and you can get X. Okay. However, because of the mod, the things change, and this is not the normal natural. This is not arithmetic log, but more of a discrete log in this particular system. This is a discrete system of mod P numbers. This is the discrete log problem, and this belief that I'm talking about, this is not just some kind of a fancy whim of someone, but this is a well-studied problem, and mathematicians and computer scientists have studied this problem for a long time, and there is some reasonable sort of basis for making the assumption that this is indeed a very, very difficult problem to crack. And nobody right now knows how to crack it. And this belief or this assumption that this problem cannot be efficiently solved is the basis of the discrete log problem, which currently forms the basis of this SSL, TLS, HTTPS, whatever. So all this, so your Google Meet is happening, and it is using some kind of a secure internet protocol, and discrete log is probably being used somewhere there. So this is the basis of discrete log of base systems. The basis of security comes from the hardness assumption of this particular problem. Now let's look at the second problem, factoring. Okay, what is the problem factoring? Take two primes, again, two large primes, P and U, compute their product, N equals to PQ, make N public, and P and Q are secret. And again, the belief here is given n, which is the product of two prime numbers, computing its factors is exponentially hard. Whatever I said about discrete log, similar thing hold here, that this problem has also been studied for a long time, and there is enough mathematical evidence to believe that this assumption is probably true, that this is indeed, factoring is indeed a hard problem in general. Okay. So these are the two problems, discrete log and factoring. So now the question comes, what happens if a quantum computer is there? Okay, so what Peter Shor nearly 3 decades ago, it was 94, nearly 3 decades ago, Peter Shor, what he did, he gave a single paper, he gave 2 quantum algorithms. For discrete log and factoring. So both the quantum algorithms used similar styles, used the similar kind of underlying tool, and both were polynomial time efficient. So what do I mean by efficient? I did not elaborate it. What is efficient here? So when I said exponentially hard, okay, so let's qualify it a bit because it will be useful. So take a prime P of, let's say, m bits, okay, and take AX from these range. So these are also m bits. Okay. B is a to the power x mod P, so B is also m bits. Okay, so all of these things, all of the information, that's P, A, B, X, they're all m bits. So when I say X is exponentially hard, it means we believe that computing X requires omega of 2 to the power m steps. That's what I mean by exponentially hard. And similarly here, let's take 2 primes which are m bits both. So then the product is also order m bits. Okay, and when you say exponentially hard, we believe that it will take at least 2 to the power m steps. So that's what we mean by exponentially hard. So Peter Shor's algorithm, both the algorithms, they were efficient, and by efficient they mean that it takes time, polynomial in n steps, and it's not a very large polynomial. It's something like, if I remember correctly, it's m squared. So that's the difference. That's why it was remarkable, and that's why it's sort of shook the entire e-commerce world, this entire world of cryptography. That here are 2 problems which we believe are hard, exponentially hard, and the internet, all our secure transactions, defense communication, everything is happens based on the assumption, the hardness assumption of these 2 problems. And suddenly there is an algorithm that uses, there are 2 quantum algorithms that can solve these 2 problems in polynomial time. And that is what the earlier speaker was saying, that if quantum computers sort of are more accessible and they become more powerful, then we should be able to solve these 2 problems, and therefore sort of crack the current whatever secure protocols, secure public key protocols that are implemented, they would all be rendered insecure. So that's why at this point, governments, NIST, and everyone, they are trying to look for better protocols that will be secure even when there are quantum algorithms, and that is the field of post-quantum cryptography that the earlier speaker was talking about. So that's a different sort of side, and if you're interested, please look that up, and it's very exciting. How do you design crypto systems that are efficient even when there are quantum computers? But today's topic is Shor's algorithm. So I will tell you what these algorithms are. In fact, I'll not tell you both the algorithms. I'll cover mainly the factoring algorithm. The algorithm for discrete log uses similar ideas, but the details are slightly different. So with that, let's jump into Shor's factoring algorithm. Okay. So, so before we go into the exact factoring algorithm, um, there is a so what Shor's algorithm does, it actually doesn't find the factor, it does something else, and that something else is not really Peter Shor's contribution. It was known to cryptographers for a long time. I mean, it's very standard tool that is used in analysis in the mathematical formulations of the factoring problem. Okay. So let's say so the formulation say is based. So the crucial result that is that I want to tell you is the following: finding factors of n is equivalent to finding a non-trivial square root of 1 mod n. Sorry. Okay. So let's understand what this statement means. What is a non-trivial square root of 1 mod n? Okay. So let's take okay. So let's take some n. Let's choose some n that is a product of 2 primes. Let's say n is 10, and 10 is 5 times 2, right? It's product of 2 primes. Okay. Now let's see what are the square roots. Let's compute the square roots of 1. In fact, let's first compute the square roots of 1 mod 5. Only one prime. Okay, not a product of prime. Let's compute the square root of 1 mod 5. Okay. So 1 square is equivalent to 1 mod 5. 1 square is 1, which is 1 mod 5. Let's see what 2 square is. 2 square is 4. Okay. That is, so everything is now I'm doing mod 5, right? 2 square is 4. 3 square is 9. 9 mod 5 is 4. And 4 square is 16. 16 mod 5 is 1. Okay. So therefore, what do I see? That 1 and 4 are the square roots of 1 mod 5. If you're doing everything mod 5, then 1 and 4, 1 square is 1 and 4 square is 1. So 1 has 2 square roots mod 5. Yeah, this is what we also do in arithmetic. 4 has 2 square roots plus 2 and minus 2. So in arithmetic also we have 2 square roots, and when you do everything mod 5, mod a prime number, everything will have 2 square roots. So I gave the example of 5 here, but you can take any prime number, and any prime number. If you take any mod any prime number, one will always have 2 square roots, 1 and prime minus 1. That's the number. Now let's next try to compute the square root of 1 mod 10. Okay. Okay. So 1 square is 1 mod 10. So that is definitely a square. Um, okay. 9 square is 81, which is 1 mod 10. Okay, so 9 square is 1 mod 10. And let's see what other numbers that are mod 10. Let's work out the numbers. Okay. Okay. So let's see. So 2 square is 4. 3 square is 9. 4 square is 16. 16 is, sorry, 4 square is 16. 16 is 6. 5 square is 25. 6 square is
Sir, it's not matching with the above row wherever you mentioned, no? 4 square 6 here, 4 square 1 above row. I'm confused.
yeah, so that is, let me take another example. This example I'll have a little I can see a problem there going ahead. Let's take a slightly better example. What happened to my pen? Oops. Let's take a better example. Let's take a better. Okay. Instead of 10, this the examples will be difficult to do. Let's take n equals to 5 times 7, which is 35. Okay. So now let's conclude the whole thing once again. Let's do square roots of 1 mod 35. So okay. So 1 square is 1 mod 35. 34 square, this is 34 is minus 1 mod 35. So 34 square is minus 1 square mod 35, and minus 1 square is 1 mod 35. So 34 square is 1 mod 45. You could also actually multiply, you could actually also compute 34 square. Let me compute 34 square. What is 34 square? 34 times 34 is 1156. Oh, I have to take more 35. Okay, so C 1156 is 33. So 1156, if you divide by 35, I'm getting the remainder 1. So therefore 34 square is 1 mod 35. Okay. Then let's take 6 square. 6 square is 36. 6 square is 1 mod 35, and the other number is actually going to be 29. 29 square, if you also calculate, you will also get 1 mod 35. Okay. So what I see that there are 4 square roots of 1 mod 35. And this is not surprising. This the fact that there are 4 squares and the fact that I could tell you immediately that it is going to be 6 and 29 is actually comes from a theorem in discrete maths known as Chinese remainder theorem. It's a very nice theorem in number theory. So if you're interested in number theory, you should look it up. Chinese remainder theorem. It allows you to very nicely, quickly tell you facts about mod 35 if you know facts about mod 5 and mod 7. So that's how I could quickly tell you that the square roots of 1 is going to be, the other 2 square roots of 1 are going to be 6 and 29. So this is not specific to 35. Anytime you have a product of 2 primes, if n equals to pq, then 1 mod n will always have four square roots. This is okay. So this is a fact. This comes from Chinese remainder theorem. Okay. Now, of these 4 square roots, one of them is going to be 1. So the first one. Let me label them as square roots. And one of them is going to be minus 1. So one of them is going to be 1 mod n. The other is going to be minus 1 mod n, right? Which is n minus 1 mod n, right? So that's number 2 that you see there, 34 is 35 minus 1. But then there will be 2 others. These are neither going to be 1 or minus 1, and these I'm referring to as the non-trivial square roots. Because 1 square we know that is always going to be 1, and minus 1 square is also going to be 1. But there is always going to be 2 other numbers, mod 35, whose square is going to be 1. And those I'm calling as non-trivial square roots of 1. Okay. So these are non-trivial square roots of 1. Okay. So any questions? Let me do it step by step. So so far I've told you what are non-trivial square roots of 1 mod a product of 2 prime numbers. Any questions at this point? Okay.
No, sir.
Fair enough. Yeah, please go ahead. Is there a question?
No, sir. No question.
So these are non-trivial square roots of 1 or capital N?
No, square roots of 1, right? 1 square is 1, 34 square is 1, 6 square is 1, 29 square is 1. So, right? So it's like, so 29 is like the square root of 1 because 29 square is 1. So
Okay,
these are all square roots of 1.
Right, sir. Right.
Okay, so these are non-trivial square roots of 1. Okay, so now what does non-trivial square root of 1 have to do with factoring? Okay. So let's say a is a non-trivial square root of 1. So a square is 1 mod n, and a is not 1 and a is not minus 1. Okay, so a square is equal to 1 mod n. That means a square minus 1 is equivalent to 0 mod n. A square minus 1, I can write it as a minus 1, a plus 1, which is 0 mod n, which means, and this means that n divides a minus 1 and a plus 1. Now, n is a product of 2 primes. I don't know what the primes are, but I know that n is a product of 2 primes. So PQ divides a minus 1, a plus 1. Now PQ, so this is the product of 2 primes, right? There is no other prime factor here. So the only two prime factors are on the left hand side, that PQ. And if the product of 2 prime numbers, they divide a minus 1 times a plus 1, then P must either divide a minus 1 or P must divide a plus 1. So one of the prime factors must divide. So P must divide one of the numbers on the right, and Q must divide one of the numbers on the right, because there is no other way the product of the 2 prime numbers on the left hand side can divide the product of 2 numbers on the right hand side. The numbers on the left hand side, P and Q, they do not share any common factor. Right? So since PQ divides a product of 2 numbers, P must divide one of the numbers and Q must divide the other number. That is the only, or both divide one of the numbers. That's the only way it can happen. Right? So therefore, I can say that P either divides a minus 1 or P divides a plus 1. So therefore, let's compute the GCD of n. I know n is given, n is public. GCD of n and a plus 1. And let me also compute GCD of n and a minus 1. Observe that a is not 1 and minus 1. Therefore, a plus 1 is not 0 and a minus 1 is not 0. Okay. Now, if P divides a minus 1, this means the GCD of n and a minus 1 is going to be GCD of PQ a minus 1, and because P divides a minus 1 and P divides PQ, right? So therefore, the largest common factor of PQ and A minus 1 is going to be P. And if P divides A plus 1, then GCD of N A plus 1 is going to be GCD of PQ A plus 1 is going to be if there's going to be P, right? So if I take the GCD of N A plus 1 and A minus 1, one of them will not be 1. There will be some common factor, and that common factor, there will be some common factor, and that common factor is going to be my P. So I have found one of the factors. So that's right. So therefore, if I know a non-trivial square root of 1, then I can find a common factor. How efficient is this process? Okay. So it all boils down to computing GCD. And how fast is GCD? Well, GCD is actually a very fast computing GCD is a very fast process. There is an algorithm which arguably is the first algorithm to ever exist. It's called the extended. Sorry, not external. It's called the extended Euclid's algorithm. Which is very fast and which can compute the GCD. Okay, so if let's say N and M are small m bit integers, then extended Euclid takes order log m time. So they're very fast. They are very fast algorithms. They are right. So they take polynomial. They take polynomial in the not log m. Sorry, mistake. Sorry. M is already the length, so they take polynomial in m steps. Right. So the running time is polynomial in the length, the number of bits in the integer, and that's what they are. So that's why they are very fast algorithms. Okay, so if you know any non-trivial square root of 1, then you can use the extended GCD algorithm to compute one of the factors, and that would break your crypto system. Okay. So right, so that's so this relationship is very well known. Everybody knew about it. Okay, what Peter Shor did was use this to design his algorithm. Okay. So let's look at his algorithm. So okay. So what does the algorithm take as input? It takes as input an n. Okay. So the first step is choose some a uniformly at random from 2 to n minus 1. Okay. Compute the GCD of an. So again, and we argued, and I just told you that GCD is a very fast process, it's polynomial time. So you compute the GCD. Okay. So two things can happen. Either GCD of an is going to be some number which is not 1. But if that is the case, then GCD, then we know that GCD of an is the greatest common divisor, right? So GCD of n divides n. And if we have found a GCD that is not 1, that means we have found a factor of n. Right? So if we compute GCD, if we get something that is not 1, then we are able to factor in. We have found a factor. Okay. The other thing that can happen is GCD of an is equals to 1. So in this case, we know that A is co-prime to N. So the algorithm now moves to the next step. So next step is find the order of A mod N. And what is order of A? Order of A is the smallest R such that A to the power R is equal to 1 mod N. So that's the order of A. The smallest R such that A to the power R is 1 mod N. Okay. So now it's not immediately clear if I mean, is it even possible? Is it even guaranteed that for any A there will be, I mean, order is well defined? Is it not even? It's not immediately clear as of now. If for any A there is going to be some R such that A to the power R is 1. Well, fortunately, there is this Euler's theorem that says that A to the power, if N is the product of two primes, A to the power P minus 1, Q minus 1 is 1 mod N. Right? So it tells us that there is at least some R, P minus 1, Q minus 1, which, right, so for which A to the power R is 1 mod N. Right? So therefore, since there is P minus 1, Q minus 1 is a possible R, but there could be a smaller R. Right? So whatever is the smallest R such that A to the power R is equal to 1 mod N, that is called the order of 1. So order of A. Let's look at some examples. This is good some examples. So let's say mod 15. So mod 15 is 5 into 3. Okay. So let's try to compute some order. So let's take a number A that should be 4 prime to 15. So 4 is 4 prime to 15. Okay. So what is order of 4 mod 15? So that's the smallest number R such that 4 to the power is 1. Okay, so let's try 4 to the power 1 is 4. So we're doing everything mod 15. Right? So let's do it here. So 4 to the power 1 mod 15 is 4. 4 to the power 2 mod 15 is 16, which is 1. Right? So we have, so order of 4 is 1. Okay, let's take another number that is 4 prime to 15. 7 is a number. Okay, 7 is 4 prime to 15. Okay, so let's try to compute order 15, order of 7. 15. So let's again go here and let's see. So 7, 1 to the power 1 is 7, which is not 1. 7 square is 49. So now we're doing everything mod 15. 7 square is 49, and 49 mod 15 is 50 to the 45. So this is 4 mod 15. Yeah. Somebody has a question?
No, sir. Somebody unmuted him. We have muted.
7 cube is, we can take 7 square, which is 4, and multiply it with 7. So that's 28. 28 is 13 mod 15. Okay. So let's now try to do 7 to the power 4. 7 to the power 4, I can just take 7 cube and multiply it with 7. So 13 7s are 91. 91 mod 15 is 1. 15. So 7 to the power 4 seems to be the fastest way to get 1. So therefore, order of 7 mod 15 is 4. So that's the idea of mod 15. So this is the idea of order. Okay. Okay. So I think I should number the steps because I'm writing things in between. So first step is choosing A, second is choosing GCD, third is computing the order. fourth step is, okay, so finding the order. So let's say I call R as the order. Okay. If R is even, sorry, if R is odd, restart the whole process, entire thing. Now that's a waste, but you can show that the probability of this happening is less than equal to half. It's a very small probability that this will happen. Okay. So therefore, right. So with a more than probability at least half, R will be even. Okay. So now, okay. So if R is even, then I can write R as 2s. This is right. So whatever is the half of R. Okay. Now you see that I know that R is 1 mod n, which implies a to the power s square is a to the power 2s, which is a to the power r, which is 1 mod n. And this implies a to the power s is a square root of 1 mod n. So at this point we have found out a square root of 1 mod n. There is, of course, there's a possibility that a to the power s is a trivial square root. So in this case, we restart the whole process. And there's a possibility that a to the power s is a non-trivial square root. Right? In which case, I've already explained to you that if I can find a non-trivial square root, then I can factor. So we are done. What did I do? Where is it? Right. Okay. So this probability, but there is this bad part of restart. If a to the power s is a trivial square root, this also you can say show that it is possible to show that it happens with very low probability. So with a very reasonably high probability, a to the power s is going to be a non-trivial square root of 1. And all of these low probabilities happen because a is chosen uniformly at random. So for a good number of a's, these R is going to be, the order is going to be an even number, and a to the power s is going to be a non-trivial square root of 1. Right? So that's the connection. So that's basically Shor's algorithm. Now it doesn't look quantum. Right? So before I go ahead, I'll probably pause here for a bit and see if there are any questions. Put the entire thing in one side. Right, so these are 5 steps. This all seems to be number theory, and there doesn't seem to be any quantum. So we'll go into the quantum part, but before that, these are the whole steps. I find a number, I choose a number, either it will be co-prime or I will be finding a factor. If it is co-prime, then I compute its order, and with some luck, the order is going to be an even number. If the order is an even number, then half of that even number, a to the power half of that even number is is going to be a square root of 1, and with some luck it is going to be a non-trivial square root of 1. And if I find a non-trivial square root of 1, then I know I can use GCD to compute the quantum factors. So that's the whole story. Okay. So this seems to be a very classical process. You should be able to write a Python program for it. Choosing a number is not difficult. Computing GCD, as said, is very efficient algorithm. Let's skip the number 3 step. If we have somehow, let's say we compute the order. If the order is an even number, I can just divide by 2. That's an easy step. Then I can get S. And once I have S, once I have S, then a to the power s. This computing a to the power s, this seems to be a difficult thing, but this can be done by something known as repeated squaring. This is again can be done very efficiently using repeated squaring. So we know A, we raise A to the power of S using the repeated squaring method to do it in a very fast way. And once I have A to the power S, I just hope that it's a non-trivial, right? I take the CD of it and I get. I mean, if it's a trivial, if it is 1 or minus 1, I'll know immediately. I'll restart. And if it is not 1 and minus 1, I'll take the GCD of this and n, and I'll get a square. I'll get a factor. That's what the algorithm is. So everything is fast, efficient, in classical. The only step that I didn't tell you is step number 3, finding the order. Now, classically, there is no better way to compute the order of an arbitrary number other than the method that I was doing on the right side. It is basically take A and raise A to the power of 1, 2, 3, 4, like this. And how many possible R's can be? Well, we know that R can be as large as P minus 1 times Q minus 1, which we don't know what it is. So the maximum possible R that it can be is the maximum possible R that you want to run the loop to is n minus 1. So you have to try order n, roughly n many trials. You need n many trials of n, capital N many trials, and right. So capital N is too much. It's exponential in the number of bits in n. So therefore the classical brute force process algorithm takes exponential time. So this particular step, and this is a classical brute force process. Just try out one R at a time. So that's the exponential time process. Okay. So this in the entire algorithm, these are the steps, and all of the steps were known to the cryptographers much before Shor. Okay, so they all of them, but this step number 3 is very difficult to do in classical algorithms, so nobody knew how to do that. And what Peter Shor actually did was to give a quantum algorithm for finding order. So that is the next thing that we are going to do. So I'm now jumping into the quantum part, and there will be some quantum notations, bracket, and these kind of things, which we have seen earlier today and yesterday. And we are going to use those things to learn about the actual quantum part of Shor's algorithm, which is finding the order. Okay, so what Peter Shor actually used, the key tool that he used for finding order is actually another sort of algorithm, another technique that was very recently discovered, roughly around like few years before he came up with this algorithm, which is called the quantum Fourier transform. So if you know the classical Fourier transform, which is the exponential form, or the discrete Fourier transform, so this is just a quantum version of it. Okay. So let's see how does this work. Suppose I have let's say I have a L qubit system. Okay. And let's take an integer k from 0 to 2 to the power L minus 1. So k is an L bit integer. Okay. Now let me write down the bits of k as k0, k1 to kl minus 1. So this is the bitwise representation of k. So this is, I can write it as in shorthand, I can write it as k. So if I apply the QFT on this k, then the expression that I get, the state that I get, looks like the following. This one, e to the power 2 pi I k times j divided by n. This is the product. is the integer product. This is J. So we get a superposition. What is the state? This is a superposition of all basis states J, right, where J ranges from 0, 0 to 2 to the power m. So it's a superposition, and the amplitude of each state and the amplitude of J is e to the power 2 pi I kj by n divided by okay. So for simplicity, let me assume that, sorry, this is not going to be n. This is there's no n here. This is 2 to the power l. There's no n here, and there's no n here. This is 2 to the power l. 2 to the power l. So the amplitude of J is going to be e to the power 2 pi I kj by 2 to the power l divided by square root 2 to the power l. And the probability, if you observe it, the probability of any J, observing any particular J, is the absolute value of the amplitude, which is e to the power 2 pi I kj by 2 to the power l divided by 2 to the power l absolute value square, right? And the numerator has the absolute value of 1, and the denominator will become 1 by 2 to the power l. So this state, if you observe, it's a uniform superposition of all the basis states. What you get, so the QFT of the single K is a uniform superposition of basis states. So this is what the QFT operation is. Right? If you are familiar with general Fourier transform, which is commonly used in signal processing, or the discrete Fourier transform or the fast Fourier transform algorithm that is sometimes taught in algorithm course. So you would recognize this term e to the power 2 pi I kj by 2 to the power l. This is, I mean, it's just essentially a quantum representation of Fourier transform. So this is the quantum Fourier transform on a single basis state. So now if instead of a single K, if I have a superposition of K, K equals to 0 to 2 to the power L minus 1, we have a superposition of K, and then if I apply QFT on it, what do I get? So all quantum operations are linear, which means I can apply them linearly, which means I can apply it in this manner: 2 to the power L minus 1 alpha K QFT of K, which is 1 by square root 2 to the power L. K equals to 0 to 2 to the power L minus 1 alpha K QFT of, sorry, there's no 2 to the power L here. 2 to the power L here. Yeah. So QFT of K will give me a 1 by square root 2 to the power L. Then alpha K will remain as it is. I'll have J equals to 0 to 2 to the power L minus 1 e to the power 2 pi I kj by 2 to the power L J. Now I can do some manipulate the summation. 1 by square root this. I get the summation of J outside, and then I can put the summation of K inside. Alpha K to the power 2 pi I kj by 2 to the power L J. Okay. So if I apply QFT on a superposition, I again get a superposition with amplitudes that look like this, some kind of expression involving the Fourier coefficients. So this is what the QFT operation is. Okay. So now what sort of shortly before Peter Shor came up with this algorithm, there were some efficient quantum circuits for QFT. So for example, it is known that QFT, this QFT can be implemented using order L square gates and depth. So, so QFT over these L qubit system can be implemented using order L square resources. So that's about quantum Fourier transform. So I'll soon connect quantum Fourier transform to order finding. So now let's go to order finding algorithm. Remember, so just to connect to you, just to remind you, in Shor's algorithm, all steps are classical except the step number 3 for finding the order, which is the real contribution of Shor of giving a quantum algorithm for order finding. So where am I? Yes. So start with a new page. So quantum algorithm for order finding. So what is the order finding problem? Given n, which is the given n in general, and some a from randomly chosen from 1 to n minus 1, such that a n are co-prime. The task is to find the order of A, which is an R, which is the smallest R, such that A to the power R is 1 mod n. So that's the order finding problem given n and this kind of things. Okay. So what? Okay. So right. Okay. So let's consider this particular operator. So let's consider this particular operator or a particular gate. Let's consider this operator UA. This gate UA, which knows how to raise something, which uses the idea of raising A to the power of something. So let's see what it takes. It's a 2-qubit, 2-register operation. So there are 2 registers. Let's say S and T. What it does, the first register remains as it is, and the second register, what it does is it multiplies the second register T with A to the power S and takes the mod n of the whole thing. And this is defined for all S from 0 to 2 to the power L minus 1 and all T such that T and N are co-prime. So it is defined on all such things. So let's, for example, suppose, okay, let's. I mean, I think this is very straightforward. Okay. So suppose one can implement this UA. So what UA really needs to do is to be able to perform this exponentiation, be able to compute A to the power S mod n. So A is known. So but S will be the input to UA, and you have to raise A to the power S and multiply it with 2. So that's basically what how you need to construct UA. So now, okay. So let's say let's compute UA on let's take a small quantum circuit. Suppose I start with 0 to the power L and 1, 2 registers, and then I apply the Hadamard transform on the first register. What will I get? I will get a uniform superposition over in the first register and 1 in the second register. And now suppose I apply UA to this, what happens? A is equals to 0 root to the power L minus 1 S. Now if you right, so it's, as I said, it's linear. Quantum operations are linear, which means u of something, summation u of a superposition is superposition of u of the individual terms. So ua on the superposition is going to be a superposition of ua on the individual terms. So it is going to be ua on S of 1, and ua of S of 1 is defined above. So it is to the power L minus 1. ua of S of 1 is S. T is 1, so there is no change, and it just becomes a to the power S mod n. Okay, so let's call this state as psi, and let's try to understand the states, the states in the superposition. So this is also superposition. Let's try to understand the states in the superposition. So what I'll do is I'll write S, and I'll write a to the power S mod n. So first register has S, second register has a to the power S mod n. Okay, so S can be from 0 to 2 to the power L minus 1, and I will make a slightly simplifying assumption. I'll assume that the order, it divides 2 to the power L. The sort of explanation when order does not divide 2 to the power L is quite complicated, and it's just messy. There's a lot of messy algebra. So to convey the basic idea across, I think it is enough to it's easier to make this assumption. Okay. So which means I can assume that 2 to the power L is R, a product of is a multiple of R. So let's say 2 to the power L is RB. Okay. So now let's look at the states in the superposition. So S goes from 0, 1, 2 like this. So when S is 0, a to the power 0 is 1. When S is 1, a to the power S is A. When S is 2, the second register has a to the power 2 mod n. So the second register, everything is mod n. I'm not writing the mod n, as in like this, but they are there. Okay. When it is R minus 1, if S is R minus 1, the second register is a to the power R minus 1. When A is R, when S is R, the second register will contain a to the power R mod n. But we know that R is the order. Therefore, a to the power the second register goes back to 1. And now you will see that this thing repeats. I wrote it incorrectly. It's R. And the first register is R plus 1. The second register will be a to the power R plus 1, which is, since a to the power R is 1, it is going to be a. Now R plus 2 will be a square. It will be 2R minus 1. It will be a to the power R minus 1. And when S, the first register has 2R, the second register will be a to the power 2R. But because a to the power R is 1, a to the power 2R is just 1 square, which is 1. So it will again get back to 1. So you see that this whole block just keeps on repeating. You just keep on repeating, and it will end with it will end with B minus. The last block will start with B minus 1R, and the first register has B minus 1R. The second register will be 1, and it will end with BR minus 1. Remember, BR is to the power L, and the second register will end with a to the power R minus 1. So this is how the states will look. Okay. So what? So therefore, let me now write this state as. Let me write this state as this state psi in this following manner. Okay. So it is 0, 1 plus 1a plus 2a square plus r minus 1, a to the r minus 1 plus r1 plus r plus 1a plus r plus 2a square plus 2r minus 1, a to the power r minus 1. So we keep on continuing like this. The last step will be b minus 1r 1, and the last step here will be dr minus 1, dr minus 1. So the states will, the state psi that I had above can be rewritten in this manner. Okay. So I'm just rewriting it, manipulating it. Now what I'll do is I will group them column wise, and I will rewrite the whole thing in a column wise manner. So it is 1 by 2 to the power n. I'll also write, that's okay. Now let me do it this way. So 1 by 2 to the power L. Okay. I will, so the states in the first column, they have everything as the second register as 1. Second state in the second column, they have everything as a in this manner. So what I'm going to do is I'm going to write it as c equals to 0 to r minus 1. So that c is basically the exponent of a in the second register, and I'm going to write it as d equals to 0 to b minus 1, which is for the rows, which is for the, sorry, for the columns. And then this state I can write it as dr plus c. Sorry, and dr plus c a to the power c mod n. You can match it up. If c equals to 0, d equals to 0, it becomes 0 and a to the power 0 mod n. So it's the first term. Now as you vary c, you go from column to column. Right? So c equals, so the outer summation that's with c, that represents which column it is, and the inner summation represents which row it is. You can sort of verify. You can verify. Let's say let's just do the second row. So so d equals to 1. So if d equals to 1, the states will look like. If d equals to 1, the state will look like r plus c r plus c a to the power c mod n. Okay. So you can see that it's going to be, if c is 0, it's the first state. If c is 1, it's the second state. If c is 2, it's the third state in the row. This is so as c is varied, as c is varied. So it's basically what you get is a row. The entire unit. Okay. So therefore, so I hope you are convinced that I can write down psi in this manner. Why did I do that? Because now suppose you measure this system. Suppose you measure the system. What happens? If you measure the system, the second system collapses. I measure the second register. What do I see? I observe a to the power c mod n for a c chosen at random from 0 to r minus 1. The second register collapses to a to the power c mod n for some randomly c. And the first register, which I have not measured, collapses to 1 by square root b, d equals to 0 to b minus 1, dr plus c. Okay, so I mean, this is just simple quantum linear algebra. I just measure the second register, it collapses to some c, whatever c it collapses to, the corresponding first register collapses to a state like this. Let's call this state as phi sub c, because it really depends on the c that came in the second register. Okay. Now let's look at the state. Let's see the amplitudes of phi sub c. I want you to visualize these states. So let's look at the amplitudes of the basis states in phi sub c. So what are the basis states? So the basis states will be 0, 1, 2 in this manner, r minus 1. Okay. So let's look at the states. Maybe that's a better way. So if d is 0, so it is 1 by square root b. And let's look at the states. If d is 0, then it is c. If d is 1, it is r plus c. If d is 2, it is 2r plus c. If d is 3, it is 3r plus c. And at the last, it is going to be b minus 1 r plus c. This is what the state is going to be. So if you look at the amplitudes, so these are the amplitudes. Okay. So if you and suppose these are the states x, this is the amplitude of x. So among the first are so the amplitude of 0 is going to be 0. We write out a little bit more. So amplitude of 0 is 0, amplitude of 1 is 0, amplitude of 2 is 0, but the amplitude of c is 1 by root b. Again, the other amplitudes are all 0. Again, the amplitude of r plus c is 1 by root b. And that's what it happens. Okay. So the states, if you look at the amplitudes, they are periodic, right? So after every r, many the amplitudes are periodic. So they are periodic with period r. So right. So the state that I get after measurement is phi sub c. That is a periodic state. Okay. And why is that interesting? Because remember QFT? Because if you apply QFT over phi of c, that's a little bit more, like it takes two, 3 more lines of calculations. What you get is right, you get a state and then you measure. What you get is a state k times b for k chosen uniformly at random from 0 to r minus 1. So if you apply QFT on this state that I obtain, and then I measure, I get a state which is a product of b. Okay, so the state will be either b or 1b, there will be 0 or b or 2b or 3b or something. It will be a multiple of b. Right. So what about the measurement observed output? Let me call it as z. Okay. Now what do I do with z? So herein comes some number theoretic post-processing, which was also known way before Shor. This is a classical post-processing. So what I do is, okay. Now this z, what is z? Z is k times b. Okay. Now, and where k is the number that is uniformly chosen from 0 to r minus 1. Now, if you have a number r, you take any number, let's say 120, right? And you want to find out the co-prime numbers less than 120, you will find that there are lots of co-prime numbers, numbers co-prime to 120. You'll find there will be a lot of numbers that are less than 120 and is co-prime to 120. Okay, so this concept comes from Euler's quotient function, which says that the number of co-prime integers from 0 to r minus 1, co-prime to r, that's omega of r by log r. Basically, it's a good number of numbers. There are a lot of numbers less than r that are co-prime to r, and that observation you can see as you increase r for larger and larger r, there will be lots of numbers which are common factors with r. So it will be very difficult for you to there will be lots of numbers which will be there won't be a lot of numbers which will have common factors, because there are only a few prime factors of large numbers, and a lot of numbers will be co-prime to r. Okay, so that means with a high probability, k is going to be co-prime to r. Of course, you don't know r, so you do not know whether it is co-prime, whether it is going to be co-prime to r or not. You cannot test, but and also you do not know what k is. You do not know k, so you cannot test whether it is happening. But you know that with high probability this fact is happening. And if this happens, then let's see what we can do. Suppose I take the GCD of z and 2 to the power l. Right? 2 to the power l we know. Right? We started with 2 to the power l. Okay, the L we chose L, so we know what 2 to the power L is. Z is the observed output, and I take the GCD of Z and 2 to the power L, which is GCD of KB and 2 to the power L. We said that we'll assume that 2 to the power L is R times B, so that is there. And the greatest common divisor, because K is co-prime to R, the greatest common divisor of KB and RB is going to be B. Okay, so which means if I divide 2 to the power L by GCD of Z and 2 to the power L, that is like dividing RB by B, it is getting R. So we got R. So right. So now if K is not co-prime to R, then you're going to get some other number here. Whatever number you get, it is what you can do is you can you can raise you can raise a to the power r, and you can check that a to the power r is 1 mod n to verify. So if suppose k is not co-prime to r, then you can easily test. This can easily be tested by using this approach. Right? So therefore, just to sort of summarize the last step. So I apply QFT on a particular state, I observe, and then I observe the register, and I get an output Z, and then I do a proof processing. What I do, I compute the GCD of Z with 2 to the power L. GCD is a fast process, and that gives me some number which happens to be B. So I divide 2 to the power L by that number, and whatever I get, I raise a to the power of that, and if it comes out to be 1, then I know that a to the power R is 1. Okay. So that's the process of finding the order, right? And let's now connect you back. So right, so if I'm able to find order, then I can right. If I'm able to find order, then the rest of the steps works out, and I'm able to find the non-trivial square root of 1. And if I'm able to find a non-trivial square root of 1, then I'm able to factor. And that's sort of the so that completes the whole quantum algorithm for factoring, the source factoring algorithm. As you can see, it has only one step, that is quantum, and that one step actually involves basically involves the quantum Fourier transform, which is a fast process because the resources require our order L square, and which is a polynomial in the length of the of n. So this with a small quantum step, which is very efficient, but we do not know any efficient any efficient classical algorithm for 3. So we do not know efficient classical algorithm for 3, but we know I described to you an efficient quantum algorithm for 3, and that's what makes this entire thing an efficient sort of way to factor down. So, so that's basically what Shor's factoring algorithm is. So I'll stop here and see if there are any questions. So as you can see, it's a hybrid kind of system, right? So partly quantum, partly. Yeah, sir, please.
Thank you, sir, for your nice explanation. Participants, if you have any questions, no session is to you. You can ask the questions. Any questions? Shall I take the call for closing? No more questions? Okay, thank you. Thank you very much. Thank you very much, sir, for your nice explanation.
Thank you for inviting me, and it was great interacting with you. So I wish you all the best for the future sessions. Okay, bye and good night.
Thank you, sir. Thank you very much. Good night. Dear participants, tomorrow also we are having same 2 sessions from 6 to 9. I hope everybody will join. Thank you. Thank you very much. The feedback link was already given in the group, and here also. Please fill the feedback link with the registered name and registered mail ID so that it is easy to track. Thank you. Thank you very much.